We will now discuss exponential smoothing, a time series forecasting method that applies diminishing weight to past data, thereby placing greater importance on more recent observations. The exponential smoothing model is a widely used forecasting technique that uses a weighted average of past observations to predict future values. Unlike simple moving averages, which assign equal weight to all periods, or weighted moving averages, which assign arbitrary weights, exponential smoothing assigns exponential smoothly decreasing weights to past data. This means that more recent data points have a greater influence on the forecast, while older data points have less influence, but are never completely discounted. The primary equation for this model is f sub t equals alpha times a sub t minus 1 plus 1 minus alpha times f sub t minus 1, which can also be understood as new estimate equals alpha times new information plus 1 minus alpha times old estimate. Here, f sub t is the forecast for period t, and f sub t minus 1 is the forecast for the preceding period. A sub t minus 1 refers to the actual occurrence in the prior period, while the variable alpha is the smoothing constant, also known as the desired response rate, which determines the weight assigned to the most recent observation. This constant can take a value between 0 and 1, with higher values given more weight to recent data, allowing the forecast to respond more quickly to changes in the data pattern. The initial forecast, f sub 1, is set equal to a sub 1, the actual occurrence in the first period. The elegance of this model lies in its ability to weight recent data more heavily, providing a more responsive forecast when faced with changes in the data. The exponential smoothing model is especially effective for data without clear trends or seasonal patterns. Let's explore an example of how the exponential smoothing model works in practice. In this case, we start with an initial forecast f sub 1, which is equal to the actual occurrence a sub 1 of 820. Our next forecast f sub 2 is calculated as the product of the smoothing constant alpha, which is 0.2 in this case, and a sub 1 plus the product of 1 minus alpha, which is 0.8 in this case, and f sub 1, resulting in a value of 820. We then proceed to f sub 3, which is calculated similarly as the product of alpha and a sub 2, 775, plus the product of 1 minus alpha and f sub 2, 820, yielding a value of 811. Finally, we compute f sub 4 by adding the product of the smoothing factor alpha and the actual occurrence in the previous period, a sub 3, 680, to the product of 1 minus alpha and the forecast for the previous period, f sub 3, 811, resulting in a forecast of 785. Through this method, we are continuously updating our forecast based on the most recent actual and forecasted occurrences, weighted by the smoothing constant, alpha. Exponential smoothing is a widely used forecasting method due to its simplicity and effectiveness. However, it is important to note that when there's a trend in the data, the exponential smoothing forecast tends to lag behind the actual data. This is because the method, in its basic form, does not account for upward or downward trends, but rather places an emphasis on recent observations. To overcome this limitation and improve forecast accuracy, a trend adjustment can be incorporated into the model. This enhancement, often known as double exponential smoothing or hot linear exponential smoothing, adds a component to capture the trend in the data, allowing the forecast to track and respond to patterns more effectively. Trend-adjusted exponential smoothing, TAF, is a more sophisticated forecasting method. The fundamental idea is to estimate both the demand level and the trend using exponential smoothing techniques. The calculation of TAF sub t, the forecast including the trend for period t, is performed by adding the product of alpha and the actual occurrence in the previous period a sub t minus 1 to the product of a minus alpha and the previous TAF estimate TAF sub t minus 1, and then adding the previously calculated trend t sub t minus 1. This essentially captures the new estimate as a weighted average of new information and old estimate, adjusted for trend. Similarly, the trend t sub t is updated by weighing the change in TAF estimates and the old trend using beta. The trend smoothing constant. Here, alpha is chosen based on the level of random variation present, while beta is selected according to the steadiness of the trend. Initial values for TAF and T are estimated to kickstart the forecasting model. In this example of trend-adjusted exponential smoothing, TAF, we are using alpha equals to 0.2 and beta equal to 0.3. To start with, we set TAF sub 1 equal to the actual occurrence a sub 1 and t sub 1 equals to 0. Then we calculate TAF sub 2 by taking 0.2 times the actual occurrence of period 1, 37. Adding this to 0.8 times the TAF sub 1, also 37, and adding the trend t sub 1, 0, which results in TAF sub 2 being 37. T sub 2 is then calculated as 0, since there's no difference between TAF sub 2 and TAF sub 1. Following this, TAF sub 3 is calculated as 37.6 and T sub 3 as 0.18. By using these calculations, we can project future periods of demand. For instance, we can estimate the demand for the 13th period, TF sub 13, as 57.06 by taking 0.2 times the actual occurrence of period 12, 54, adding this to 0.8 times TF sub 12, 54.83, and adding the trend T sub 12, 2.39. Thus, the TAF method allows us to smooth out fluctuations and identify an underlying trend, which significantly improves our demand forecasting. The mean absolute deviation, MED, provides a statistical measure for comparing the accuracy of various forecasting techniques on a particular set of demand data. For example, in a comparison conducted by PM Computer Services, the MED for exponential smoothing with an alpha of 0.2 was found to be 5.94, whereas for adjusted exponential smoothing with the same alpha and a beta of 0.3, the MED was 3.97. This comparison shows that adjusted exponential smoothing outperforms simple exponential smoothing, as evidenced by its lower MED score. It's common to use relatively small values for alpha and beta in these calculations. To further enhance forecasting accuracy, this constant can be adjusted to minimize the estimation error. Additionally, estimating initial values for TF sub 1 and T sub 1 can improve the forecasting outcome.